Thank you for joining. The session is on Cradle CFD, what's new in the latest release. We expect a new release in the upcoming probably couple of months or so, maybe even shorter. So in this session, these are some of the highlights of the new release. And this session, the parts in blue are the ones that I've marked as its features that has been added, but it's somewhat less relevant, at least to the local market and the people that I know that use the software locally, at least. So it doesn't mean it's not important. It simply means I'm not going to spend too much time and effort on these. So this session is going to be more on existing clients and interested parties that I know of and features that I expect to be of use to them. So in brief, there's over the last couple of releases been quite a lot of development on modeling of batteries. So think batteries for an electric vehicle, the cooling, outgassing, all kinds of interesting stuff related to that. Then for in the session, we'll then talk about AI and machine learning, some of the capability that's made somewhat easy, at least in this release. It used to be a bit more work to get this done. And then we'll spend time on some meshing related issues. This is something that's always of import to people that use CFD. And then a new solver that not everybody knows about. So it's the scFAST solver. So we'll briefly talk about that, and then some solidification and melting models. And then for SC-Stream, some additional material models and methods that's been added and changed and so on. And then just a little bit about scPOST, in other words, looking at the results. Now this is using this AI and machine learning data. Okay, so let's dig into this pretty much from the start. So the first one will be reduced order modeling. So that has to do with artificial intelligence. So the intent behind the process is we build and run a series of detailed models with different parameters. In this case, the example that you'll see later on will be for two or multiple inlet temperatures and multiple inlet velocities. So a series of these analyses was then performed. It's transient analysis. And from there, the information is then sent to Odyssey. And in this release, what's made easier is in the AC monitor, you can now create those 3D ROM, three-dimensional, and this is the reduced order models, the info that is sent to Odyssey. So Odyssey will do the fitting, and at the end, we can then read that data back in and very quickly, in the order of seconds instead of hours in some cases, run an estimated behavior, estimated model to see what we expect analysis would have been if we did the full analysis. So it's not perfectly accurate, but it's a really good interpolation method, and it's useful to find those special kind of cases that we may need to look at in a bit more detail. If you now look at meshing specifically, so the Octree, if you're not familiar with it or you haven't used it in a while, the Octree is where we specify what size the mesh is going to be once we create the mesh. So the Octree is really fast to create with simply these hex-shaped elements. And if you want to mesh finer, it subdivides in two directions, subdivides it again, and so on. Now, previously, the options we had to create this was in the basic settings, global parameters, maximum size, and so on. And then some detailed setting where you can say, arguments like this, heatsink fin, close to the surface, mesh width, and then some kind of a smaller size. And then also some, how quickly it should transition. So in other words, fine, going coarser, coarser. How many elements does it take to go to that coarser level? There's been a feature that was added, an angle settings to capture radii and stuff, smooth curves a bit better. But in this one, what was added was local refinement based on proximity to something else. So it can either be proximity to itself or proximity between different parts. So the problem with this is, let's say this is typically the size of element I want to use. If I try and fit this in there, I'll maybe fit one element there, maybe not even one. So we'll end up with not enough elements through that thin section to capture the behavior at all well. So in this method, what it will do is we can specify some kind of a dimension, say for this kind of stuff, refine it so that there's significantly smaller elements in that region. Now, previously, I could have done something similar by saying for the outer surface of this fin, refine it to that level. But if I kept it at that, it would have then immediately transitioned to larger elements and then the smaller elements again. So the next level would then be to say, use more than one layer for that fine mesh. But the problem now is it's going to grow in this direction, in that direction. And if this is something, a part of a larger part where there's regions we do not want those smaller faces, it's going to be an issue. So in this case, we specified only in small gaps. Refine the section there, or where there's two parts, two faces close to each other. Now, this is probably a more common case. It's some kind of a curved surface coming close to, it can be a flat surface, a rigid or a flat surface. It can be another curved surface. So here's a great example. If you have something like the wing of an aeroplane with the elevator that's, or the aileron or whatever inside there, and that's got a very small gap in between there. So let's pretend that green part is, let's say, the aileron, and this yellow part there is part of the wing. So it's probably going to be curved as well. There's going to be some regions where there's a very small gap and a bit further away, a larger gap. If I try to do the same, I want to fine mesh only in that small region, I would have needed to previously split this face into these separate regions, and I would have needed to figure out where it's actually close to something else. If I made a mistake, I need to try again and try again until I get a great mesh. So with this now, it simply says refine it to that level and have enough elements there. Automatically from there to there, it grows larger and larger elements. So that makes it a lot simpler then to capture these local elements really well, local regions really well. There's a second parameter or second settings related to this, which is not part of the meshing, not part of the Octree, it's part of the meshing itself. So in this case, there's an option that says we still have, and we can see we've got large elements there, same size as these, but these are kind of like boundary elements that was then extruded all the way up to there, where previously we would have tried to fit those kinds of elements in there with this large setting. So again, this is a great example for that aileron and wing example. So again, let's say the aileron and the wing will probably be closer to something like that maybe. But the problem is if I refine the mesh using the previous approach, this means I'll have smaller elements in two directions. It doesn't. But what we typically find is that the region there starts to utterly dominate the mesh in terms of number of elements. That finer mesh requires finer mesh there than I would have needed, which in turn needs finer elements there. But it's not just in one direction, it's in all three directions. So if I take a mesh, a hex element, and I halve it in all three directions, I end up with 8 times as many elements. And that's not the problem. If I go there, instead of argument's sake having 1,000 elements, one level refinement would be 8,000, then 64,000, and very quickly that blows up to 500,000 elements for one of these small regions. And that's assuming that 1,000 elements was actually the initial correct value. If that was a bit larger, really quickly, this becomes of the order of millions of elements. So this is the alternative approach, and both of them can work together. But in this case, we still have large elements all the way through there. So we don't actually refine the average size, but in the thickness direction, it just generates these apologies, talking too fast, these thinner elements, which allows us to then have significantly less elements in the mesh compared to having to refine this in all three directions to get that same size. So the next change or improvement that was made was with the voxel measure. The facets, that's a part of that processing to convert from your geometry to the mesh. That faceting approach is now done in parallel, and the speed up is maybe not awesome, but really significant. So it goes from, as an example, this is 2 separate models, goes from a bit over 2.5 hours to significantly less than, let's say, an hour and a quarter, 3/4. Similar models, so there's between 30 and almost 40% reduction in the time to mesh. So this makes it a bit faster than to use this method and to get to a good quality mesh and in a reasonable time. Then something that I think a lot of people may not know about. Previously, it was not possible to run any of the Cradle software on any of the GPU hardware. So specifically the Tesla series, not the graphics cards. There's a specific solver that was released with the latest release, scFAST, which is a version of SCStream, but specifically optimized to run and use GPUs. So again, I have to say that it's not your typical graphics card. These are for the Tesla cards. In this example, the A100 and GH200, relatively expensive cards, but the main advantage is one of those cards you put into a PC and you get a speed up from 96 cores on a single node, 3.5 times faster if you have that card, or 6.7 times faster with this. So this is in a single machine. Also, you don't need to set up NPI and all kinds of interesting stuff. In this example, just to show you what happens if we double the number of cores by using a second node, speed up is significant, but it's still less than these would have been. In terms of cost, I think with the AI exploding costs everywhere, it may not be that cost efficient, but the main advantage will be it's much easier to set up, much smaller setups, and easier to effectively then use. Okay, so this is the GPU acceleration that's available then with the latest version of Cradle CFD. Just a quick slide. I've added some changes to phase changes, so conditions for solidification and melting can now be set. So you can now run a simulation where the ice melts, causes a liquid, and possibly even evaporate, if you're interested in that as well. Okay, here's a very interesting slide. One of the nicest videos I've seen in a while, to be honest. So it shows the laser modeling approach that's available in scStream. So the top one, 2 parts being welded together at the top. The bottom is there's an aluminium part on the left-hand side that's not shown here. So you're welding the 2 parts together. So it's effectively able then to model the welding process and to model the heating due to laser. Another interesting material is phase change materials. So we're used to thinking for phase change as something like water going from ice to liquid or liquid to gas. And the amount of energy that you need to change that phase is really significant. So let's say you have ice at -2 degrees Celsius, you heat it up, it goes warmer and warmer until it starts to melt. And then while it's melting, the temperature doesn't really change. So it kind of fixes it there for a while. And then at some point it starts, once it's fully melted, it now starts heating up again. Now, there's certain solid materials that undergoes a phase change, similar to what steel would do, argument's sake, between martensite and austenite and bainite and all of those. But in this case, there's a really significant amount of energy absorbed in order to perform that phase change. So these are typically used in usually some kind of a high-tech fields where we need to absorb a lot of energy for a short duration. So I've seen some of this kind of stuff in rocket engines, for example, where it's used to any part inside there will heat up too much argument. So by using a phase change, the temperature doesn't change by the same amount. So it heats up, stays constant for a while, and then heats up a bit further. So this is the ability to model this. Now, previously, you could have done this by specifying a CP value that just changes by a massive amount at a certain temperature, but it's a very inefficient way. The method that they've implemented here is specifically to do phase changes and is much more efficient. So there's an example. If you look at the temperature change, if I pause and rewind again. So this is how much of the different phases exist. So compare the first two in terms of temperature as time changes. You'll see the second one with the phase change material changes a lot slower. And then at some point, it starts heating up quickly as well. Another feature that was added in SIStream and eDesigner, and the difference between the two is eDesigner is simply a subset of SIStream, so they're effectively the same software, is that there's actual fan modeling that can be done now. Instead of using a rotating frame, you define multiple reference frames. So we define this fan as moving in a different reference frame to everything else. So this allows you to calculate the flow through the fan, over the fan, and so on, without having to use a mesh that slides or moves relative to another mesh. So the advantage is that it pretty much runs significantly faster while giving the same answer. Okay, the last slide I have is on result post-processing. And this is using that results, those 3D ROMs that we initially created, that reduced all the models we got from from Odyssey. So we've created, this is my initial set of runs that was done, different inlet temperatures, different flows. So display that you'll see different temperatures, different flow rates, and so on. So there's velocity of half, 1 and 2 meters a second, and different temperatures as well, anything from 40 up to about 80 Celsius. Now, if I need to know at a different temperature, let's say 75 argument's sake and 0.75, I need to do a full-on analysis. If I use this method, it creates the AI model of this traditional model. And now in the post processor, you can specify pretty much any temperature and inlet velocity, interpolate, and it creates a new set of time steps. So this is now at a different inlet velocity and temperature than any of these was initially. So there you can now see in 3 dimensions what the expected flow behavior would be. Okay, so that brings me to the end of the session. It's been a short session, but again, there's quite a few additional features that was added, which I don't think would have added too much value to try and dig too deep into them.
Thank you, Gerrit. That was short and sweet, I think. If there are any questions, you're most welcome to put it in the chat or email us. So the next session will be on Adams, what's new on the 5th of June. So if you're also interested in Adams and what is new in Adams, please join us again on that Friday of the 5th. Thank you everyone for attending. We've recorded the session and it will also be published on our YouTube channel along with the other lunch and learns that we've already had. Thank you. Bye-bye.